Hello. Now we're back to more probabilities. So this section, we're talking about tree diagrams, which are helpful when you're trying to calculate probability and there's more than one event happening, I guess. So yeah, it's like if there's one event that transpires and then another one, and you want to know the probability that both happen or neither happen or one and not the other, something like that, then tree diagrams are pretty helpful for multiple events. Yeah, maybe that would help to even say that. Useful in probabilities with multiple events. Okay. So first thing that would help us is up here we have the multiplication rule of counting. Okay, it says the total possible outcomes are found by multiplying the options. So let's see, in other words, if there are m distinct ways to perform one experiment, and that's a number, m is some number, and n ways to perform another experiment, then there are m times n distinct ways to perform both experiments. So it's, anyway, so we won't calculate probabilities yet, but we'll just practice using this multiplication rule, which will help us with probabilities. So first example, it says Brian must dress up for his job interview. He has 3 dress shirts, 2 ties, and 2 pairs of dress pants. Okay, let's see. How many possible outfits does he have? Well, I guess there are 3 ways to choose his shirt, since he has 3 shirts, and 2 ways to choose his tie. Ways to choose his tie, and then 2 ways to choose his pants. Okay. So the multiplication rule tells us that we just take all those numbers and multiply them. 3 times 2 times 2 will give us 12. So there must be 12 possible outfits. And then we'll see, we're going to draw a tree diagram pretty soon that'll kind of show why that is. And yeah, I think we'll start to believe it. And you notice it's not just if there are 2 events. If there are 3 events like this, dress or shirts, that's one event, tie is another event, picking his pants is a third event. So even though there's more than 2 events, you still multiply them together. So even though the multiplication rule only says when there are 2 events. So it'll be similar here. At a restaurant serves 5 main dishes. Okay, so 5 main dishes, 3 salads, 4 desserts. They want to know how many different meals can be ordered if you choose a main, so one event, you don't have to write this out, but you could say event 1 is to choose the main, and then event 2 would be choose the salad. You can even make it shorthand by writing E2, and then event 3 would be to choose the dessert. Well, then the total number of possibilities would be the 3 multiplied together. 5 times 3, okay, that's 15, times 4 is 60. So there's 60 possible meals, I guess, total. That's a lot for only having 5 main dishes, 3 salads, and 4 desserts. Let's see, how many license plate numbers consisting of 3 letters? Okay, so I'm going to maybe make little spaces here. These 3 are letters. And then followed by 3 numbers. Okay, 3 numbers. And I guess by numbers they mean digits, huh? Each of the numbers won't be more than 1 digit. I might even say digits. Okay, how many are possible when repetition is allowed? So that means that if I chose, say, an A for the first letter, an A could be the second or the third letter also. It's not like once you choose a letter, you can't choose it again. So let's see, for letters, how many letters are in the alphabet? 26 letters in the alphabet, right? I think. In the alphabet. And then also you multiply by the next letter, there are 26 options also, because you can repeat. And the third letter, there are also 26 options. As far as digits go, you have 0 through 9, right? That's actually 10 different numbers, because 1 through 9 is 9 numbers, and the 0 makes 10. So each of these digits would have 10 possibilities. Wow, that's a lot. I think I'm going to have to use a calculator for that one. Especially the 26 times 26 times 26. Okay, let's see. 26 times 26 times 26 times 10 times 10 times 10. I'm getting 17,576,000. Wow, that's a lot. Yeah, so if you wonder, how come they don't run out of license plates? Well, I think you can see why. There's 17 million possibilities. Okay, now let's make it more interesting. How many license plate numbers consisting of 3 letters, okay, so far, same thing, 3 letters and then 3 numbers or digits are possible when repetition is not allowed? Okay, so repetition not allowed, that means there are 26 options for the first letter. Okay, but say you chose a letter, I don't know, just pick a letter in your mind. Let's say K. I don't know. Okay, then how many options are there for the second letter? There's 1 less option for the second letter because you can't choose the same one you just chose. Option for the second letter. That means there are 25 options. Alright, and then for the third letter, I can't choose the letter I chose for the first one or the second one, so there are only 24 options left. After choosing the first and the second letters. So it'd be 26 times 25 times 24. And then for the digits, I assume they're saying the same thing. Like we said in the last one, there are 10 possibilities for the first digit, but then there'd be 9 for the second digit, because you can't repeat. No repeated digits. And then for the third digit, there must be 8 options, because you can't choose the same one you chose for the first one or the second one. That's 2 fewer options. Alright, so when they say repetition is allowed or not allowed, that makes a big difference. So, okay, let's multiply these together. 10 times 9 times 8. Okay, wow, that's a lot. Still a lot, but not quite as much as when repetition is allowed. 11,232,000. That's quite a bit. Wow, so keep that in mind. Yeah, when repetition is allowed, you can keep using the same number. Like, if you have a bunch of letters, you just multiply 26 together. But if repetition is not allowed, then you can't do it that way. There's more thought involved. You have to decrease by 1 every time. So, okay, and that brings us to tree diagrams. So tree diagrams are a visual display of the total number of outcomes of an experiment consisting of a series of events. Using a tree diagram, you can determine the total number of outcomes and individual outcomes. So I guess if you want for that, the meal example, which one was that above? I think I said there were 5 mains, right? 1, 2, 3, 4, 5. You're choosing your main. Okay, there's, I don't know what they are, salmon, beef, chicken, whatever, I don't know. And then for each of those, what do you have? And we were supposed to pick a salad, right? How many salads were there? 3 salads and then 4 desserts. Okay, so once you choose your main, each of them has 3 options for salad. See, I'm already running out of room. 3, 3, 3, 3. So those are all the 3 different types of salads depending on your choice of main. And then for each of those salads, you had 4 choices of dessert. So you can imagine how complicated this is getting. 4 little branches for each of those. See, I should have made a bigger one. All kinds. That's the idea. You show a branch for each of the options for the first event, and then from each of those branches, you should have an option for the second event, and then on and on and on. And then you can calculate probabilities a little easier, or you can calculate the number of options easier. So let's see. Example 5 says, Jacqueline is in a nursing program and is required to take a course in psychology and one in physiology, A and P. What the hell is that? Whatever. Next semester. She also wants to take Spanish too. According to the course catalog, there are 2 sections of psychology, 2 of A and P, and 3 of Spanish. How many different class schedules are there to choose from? Okay, well, they didn't say to make a tree diagram yet, so I'm just going to multiply them together. There were 2 sections of psychology, and then there were 2 of A and P, and how many? 3 of Spanish? 2. So that makes 2 times 2 is 4 times 3 is 12 total possibilities. Okay, so now in part B we'll draw a tree diagram just to show why. It kind of shows why the multiplication rule is the way it is. So let's see. Choice number 1 was which psychology class to choose. So this is the start. This is her. She's going to choose one of the 2 psychology classes. Let's say oops, I spelled that wrong. Psych 1 or Psych 2. I mean, they're not different classes, I'm just saying option 1 or option 2. And then from each of those, we have 2 options for A and P. A and P1, A and P2. They're just different sections of the same class. And then if she had taken psychology, the second section, she would also have the same choice, A and P1 or A and P2. And then from each of those branches, there are 3 possibilities for Spanish. So each of those little tiny branches should have 3 even smaller branches coming from them. Spanish, the first Spanish, the second, the third. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And you could say Spanish class 1, Spanish class 2, Spanish class 3. Same thing for the second option here. Spanish class 1, Spanish class 2, Spanish class 3, 1, 3. Okay, so that was the last event, right? Or the last choice she had to make. So you can just add up the total. Add the total number of branches you're left with. There are 12, I think. Anyway, so you could write it out like that with a tree diagram. That's why the multiplication rule is the way it is. It just kind of proves that that works. So, okay, let's see. Let's try example 6. This is going to involve tree diagrams and then probability also. There are 2 archers. Lee has a 3/4 probability, or 3 out of 4 probability of hitting a target, and Yuka, I hope that's how you say that, has a 4 out of 5 probability of hitting the target. So first we'll draw a tree diagram, and then we'll see what to do. So here's the start. The first thing they mention is Lee's shooting that. So hitting that, let's say she hits the target, or she doesn't. That's really all that can happen. Doesn't hit target. Okay. And then now that we have probabilities involved, they've actually told us, I'm going to put those in the tree diagram as well. So they said she has a 3 out of 4 shot of hitting the target. So if her taking that branch would be a chance of 3 out of 4. How about not hitting the shot? Well, remember, the probability of something not happening is 1 minus the probability of it happening. So if I want to know the probability of her not taking the shot, it would be 1 minus through 3/4, which was the probability of her taking the shot. And that'll give you 1/4. So I know I have a 1 out of 4 probability of her missing the shot. Just keep that in mind, that all the branches should add up to 1, I guess, if you think about it. All the vertical branches. Vertical branches should add to 1. That might help a lot. Okay, then there was, I should say who that was, huh? Because there are 2 people here. Lee hits the target, Lee doesn't hit the target. Okay, and each of those, it's almost like, what's it called, a parallel universe. In one universe, let's say Lee hit the target. Well, then there are 2 possible things that can happen for Yuka. Yuka hits the target, or Yuka misses, I guess you could say. And then in the parallel universe, Lee doesn't hit the target. Both of those things can also happen. Yuka hits the target, or Yuka doesn't hit it. Misses. And you could have said misses or hits it, whatever you want to say. And what they say the probability was 4/5 that she hits it. So 4 out of 5 that she hits it. Then what's 1 minus that? 1 minus 4/5 is 1/5. So that's how I figured this guy out. It was 1 minus 4/5. Same formula as before. And then Yuka hits, we already did that, 4/5. Yuka doesn't hit, that was 1/5. So we got the tree diagram. Now if you want to look at part B, if they both shoot simultaneously, what is the probability that they will both hit the target? Okay, so what we need to do is identify the path described, because they both want to hit the target, then multiply the probabilities, and that'll be what we want. Okay. So let me see. It might be helpful to highlight. They both hit the target. Okay, that means from the start, Lee's going to hit the target and Yuka's going to hit the target. So I went down that branch. And once I've highlighted the branch that I want, I'm going to multiply the probabilities together. It was 3/4 probability that Lee hit the target, and then 4 out of 5 probability that Yuka hit the target. And you could multiply across, but those guys are going to give you, or they're going to reduce to give you just 3/5. So there's a 3 out of 5 probability that they'll both hit the target. And then we can look at if Lee hit the target but Yuka misses. Okay. Well, if you want, what we can do, just to be safe, is part B, I'm going to remind myself, I highlighted that path in blue. Maybe part C, part C I'll highlight in yellow. Lee hits the target, that means we took the same path initially, But then they said Yuka doesn't hit the target. That means we're taking this other path. So we're going to look at the 3/4 and the 1/5 instead. 3/4, because Lee hit the target. 1/5. Yeah, probability Lee hit. And this is the probability Yuka misses. Okay, and those, you're not going to be able to reduce that, so you might as well multiply across. Let's see, a lot smaller probability, huh? Alright, what about part C? Or sorry, part D. Yuka hit and Lee will miss. Okay, where was that? Well, Yuka was mentioned second, so I'm going to think more about Lee will miss. Lee will miss is this way, and then Yuka will also, wait. Yuka's hitting, okay, so that means that we go this way. Okay, so the probabilities along that path are 1/4 and 4/5. Let's multiply those guys together. 1/4 times 4/5, and then cancel the 4's to leave with 1/5. There we go. Alright, last one. They will both miss. I think that's the only path we haven't looked at yet, right? Let's see, Lee misses, that would be going down this path. And then Yuka misses, that would be going down this path. That's the two probabilities we hit were 1/4 and 1/5. I'll multiply those guys together to get 1/20. There's not much of a probability of them both missing, huh? One of them's probably bound to hit it. Alright, that's almost done here. Let's try example 6. Carl is not having much luck lately. His car will only start 80% of the time. Okay, his car will only start 80% of the time, and his motorbike will start only 60% of the time. We'll draw a tree diagram. Okay, well I guess they mentioned the car first. So here's start. Let's say car starts. Car doesn't start. Okay. And then for each of those, I guess, parallel universes, his motorbike could start. Like, starts or doesn't start. Motorbike doesn't start. And the parallel universe where his car didn't start, his motorbike could start. Like, starts. Or it could not start. Doesn't start. Alright, so that's a lot of options. And you might as well throw the probabilities in there. So I notice they gave us the probabilities in percentages, but like we saw in the previous section, when you're doing math with probabilities and you see percentages, it's better to use decimal. So I'm going to change the 0.8 to a decimal, and also this 0.6 here. That would be a lot better, or 0.60, whatever you want to think of it as. So there was a 0.8 probability that his car started, and then a 0.6 probability his motorbike started. Well, if there was a 0.8 probability his car started, the probability his car doesn't start is going to be 1 minus that, because we know that the probability of the opposite of something happening is 1 minus the probability of it. So 1 minus 0.8 would be 0.2, or 0.20. There we go. And like we said, you can check by adding those together. The probabilities vertically should always add up to 1. Okay, and then same thing with the motorbike. Once we get there, he has 0.6 probability of the motorbike starting. 1 minus that is 0.4. So that would be the probability of it not starting. There we go. And then these are the exact same. This is his motorbike starting. This is it not starting. Okay, so we got it. Alright, nice. So how about part B? Using the tree diagram, what is the probability that first both will start? Okay, well we know how to do that from the previous problem. I'm going to highlight that. Both start, that means I want the car to start. I'm going this way. And I want the motorbike to start, so I'm going this way. Okay, the probabilities along the way are 0.8 and 0.6. If I multiply those, I get 0.48, which if you want to convert that to a percent, since we were given percents, that'd be a 48% chance. Or I guess probability. Not very good. It's kind of almost got a 50-50 shot, huh? And then the second part, they say, what is the probability that he has no choice but to use his car? Okay, what the heck does that mean? It means the motorbike does not start. Okay, that's a good one. So notice that there are two parallel universes. One where the motorbike doesn't start. He could have gone this way, or he could have gone that way. So it could be, they didn't mention the car. Does his car start or not? Oh, wait. Oh no, the car has to start, right? Hello. He has no choice but to use his car. Okay, if his car didn't start, I don't think he could use it, right? Never mind. So this doesn't make sense. It'd have to be the yellow path at the top. Yeah. How could he use his car when it doesn't start? Alright, so the yellow path, we had a probability of 0.8 of the car starting, and then a probability of 0.4 of the motorbike not starting. If you multiply those guys together, you get 0.32, which you can convert to percent by writing 32% probability. Alright, well, it's better that the probability they both start is higher than the probability that one won't start, right? That's a good sign. Alright, so hopefully everything's making some sense so far. These definitely take some practice just to get used to it. So let's try the very last example. Bag A contains 3 red and 2 yellow tickets. Bag B contains 1 red and 4 yellow tickets. A bag is randomly selected by tossing... That's okay. Okay, so it sounds like there are 2 choices here. So I'm going to say start. You either choose bag A or bag B. I think that's your first choice. Alright, then from there, let's say you chose bag A. There are 3 red and 2 yellow, so you're either going to get a red ticket or a yellow ticket. So a red ticket or yellow ticket. And if you're wondering about the numbers, you know, there are 3 red and 2 yellow. That'll help us with the probability. So let's see, and then if you chose bag B, where'd it go? There was 1 red and 4 yellow, but still the same choices. Either you get a red ticket or a yellow ticket. Alright, now let's think about the probabilities. Okay. So first of all, you choose bag A or bag B. They didn't say anything about probabilities, but I just imagine you have a 1 out of 2 shot, or, you know, 50-50 shot of getting bag A. There's only two bags. Okay, so there's only 2 bags. So the total options are 2, and you have a 1 out of 2 shot. But as far as the tickets go, okay, let's say you grab bag A. And how many tickets does bag A have total? They said there were 3 red and 2 yellow. 5 total tickets. Okay. So there are 3 red out of the 5. That means you have a 3 out of 5 probability of getting a red. And then for the yellow tickets, there were 2 yellow out of the total of 5 in that bag. So you have a 2 out of 5 shot. In the other bag, bag B, there were also 5 total tickets. 1 red and 4 yellow. So for red, you have a 1 out of 5 shot because there was only 1 red out of the 5. For yellow, you had 4 out of 5 shot because there were 4 yellow out of the 5 tickets. Okay, beautiful. So we drew the tree diagram with the probabilities. Now let's see, part B. Determine the probability that the ticket is yellow. Ah, okay. That's a good one. So notice that there are 2 paths. This is the first time we've seen this, where you could have chose bag A, because it didn't specify which bag to choose. Okay, 2 paths. You could have chose bag B and grabbed the yellow ticket, or bag A or bag B. So what we'll do is we'll figure out what's the probability of going this way, bag A and a yellow ticket, and the probability of going this way. Okay. So we'll calculate the probabilities individually, then we'll add them together afterwards. Okay, yeah, so that if you're ever calculating the probability with the tree diagram, and there are 2 possible paths, like here, you know, they specified they want us to have a yellow ticket, but they didn't specify which bag. That means that there are 2 paths we could have gone on. We'll just figure out the probabilities of those paths, and then add them together. That's it. Almost like expected value. Remember expected value? You can multiply probability times value. Okay, so the first one, so let's highlight that first path. So you could get the yellow ticket by going bag A. Let's see, so that could be bag A, and then yellow ticket. So let's calculate that probability first. And like we did in the previous problem, you're just going to multiply the probabilities along the way. So there was a half. That was the probability of getting bag A, multiplied by 2/5. That was the probability of getting a yellow ticket. And that you can reduce while you're there. The 2's cancel just to leave 1/5. So that'd be the probability of going bag A and getting a yellow ticket. But you could also get a yellow ticket by going by bag B. So where did that go? We went bag B, and then a yellow ticket was this way. So let's look at those probabilities and multiply them together. It was 1/2 times 4/5. 1/2, 4/5. Now you can reduce a little bit. That's going to give you, this 2 goes into 4 twice. You multiply across, you're left with 2/5. So you have 1/5 and 2/5 together make 3/5. There you go. So there's a 3/5 probability, or 3 out of 5 probability of getting a yellow ticket. I think that's probably as complicated as tree diagrams get. It's if the thing they ask for, the probability of, could be obtained in more than one way. You just have to figure out which paths will get you there if there's more than one, and then add them together, or add the probabilities together once you calculate them. But not too bad overall.